Hi folks, Mr. Long here with the final video on computations and interpretation and reasoning with three-dimensional vectors. So the next question we're going to do is we're going to do some vector addition. It's no different than in adding in 2 dimensions, but we just need to get some practice representing vectors in 3 dimensions. So if I had a vector from A to B, which is represented here, that's A to B right there, right? And if I want to add that to 3 of CK. So C is here, right? And K is all the way up there. So I want to add those vectors. So what I've got to do, first of all, is I've got to get what those vectors are. Okay, in 3-dimensional space, delta X, delta Y, delta Z. That's how we represent vectors in what's called the algebraic or Cartesian form. So in this case, delta X, look at the first vector. Does X change at all from A to B? Sure it does. It changes by 2. So X changes by 2. What does Y change by? No, nothing up and down. A and B are at the same height with respect to Y. What about Z in terms of the distance away from this axis right here? It's also 0. Okay, so 0 and 0. Then we need to do vector CK. Well, CK, for X, I have to go all the way from one end to the other end of the rectangular prism. And that would be a distance of -4, okay, because I'm going towards the origin. What about delta Y? Delta Y goes from the floor, if you will, all the way up to the top. So that's a unit, that's 2 units up, so delta Y is 2. Delta Z, what would delta Z be? Well, I start out 2 units away from the XY plane, and I end up right on it. So Z goes from a value of 2 to a value of 0. So that's going to be -2. Okay, so that's how I'll be doing it. So I'm going to add those vectors together now. So 2, 0, 0, plus 3 of this vector. So remember that means delta X, delta Y, and delta Z all need to multiply by 3. So that's going to become -12. 3 times 2 is 6. 3 times -2 is -6. Okay, so finally I need to add up my components, the X components first. 2 plus -12 is -10. 0 plus 6 is 6. 0 plus -6 is -6. And that, folks, is the vector that I should put it here, that equals AB plus 3CK. Okay, so that's how you add vectors in components in 3D with, remember what this is, a scalar multiple. Okay, so here's one that gets a little bit more reasoning based. So what we're going to do is create a vector sum or difference with these. We're going to have some questions here that we have to create vector sums or differences. So it says right here, the answer to a vector sum is the vector from B to the midpoint of DI. Okay, so from B to the midpoint of DI. So that's right from here to here, okay? So that's vector, that's the vector. So we want that to be an answer. Now I'm calling this point here B prime. So the vector starts at B and ends at B prime. I know that's not the correct name, but just for this I wanted to do it that way. So now what I need 2 vectors that are going to take me from B to B prime. Now this is what's interesting with this stuff. So I'll do these in different colors. So I need 2 vectors to get me all the way from B to B prime. So watch this. I can make one vector along the floor. That takes me to D. And then I need another vector to take me up to there. Okay? So that's using triangle addition with vectors. We're not going to spend as much time on that as we would normally. Again, it's not about normally. It's that we're going to focus on algebraic vectors and not geometric ones. But you can see that you start at B and you end at B prime. It doesn't matter which route you go, right? But that's vector addition right there. So either way, you go from B to B prime. So that's why it is vector addition. So let's write that down. So what's that first vector start to finish? Well, it's B to D. What's the second vector? It goes from D to B prime. Okay? So you can see that. Then what about B? Oh, and what I can do, folks, is, you know what, I think I might leave it there, but the other thing we could do is, you know what, let's just leave that. Let's leave that for now. Let's leave that now. By the way, that's called directed line segments when you name it that way, just with letters. Okay, so this one here. Now we're going to do a difference. So we're going to do a difference of two vectors is JC. J to C. Okay, so what I'm going to do here is just, I'm going to erase some of this work here so it's a little bit easier to see. Okay, and so our answer in this case is going to be J to C. And we're going to use this idea of add the opposite. So first of all, what we're going to do is we're going to create vectors that add up to JC. So this is, again, fairly straightforward. We can take a vector that starts at the tail. Remember, that's the tail up there. And then I need another vector that joins it. So you can see the triangle again that you've formed. So what we've got here, folks, is vector JC happens to be, so this is J up here. So J, and that is, I can't tell what that is. What is that point? E, sorry, that's E. Okay, so we're going to go, JC is going to be the same thing as J to E plus E to C. But we know with vectors that we can add the opposite, right? That's subtracting. Well, we know with anything, subtracting is adding the opposite. So what I can do is, it can be plus negative, so it's J to E. What's the opposite vector of E to C? Well, the opposite vector of E to C is C to E. Okay, C to E. Let's think about that for a second. So I'm going to do this. I'm going to write this down here. What's vector AB? Vector AB is 2, 0, 0. What's vector BA? Now I'm going from B to A. Well, what happens now? Now it's just negative 2, 0, 0. So here's what happens. This is what the idea of opposite vectors is. So if I take a vector AB and I write a vector BA, it just goes in the opposite direction. It's the same length. It'll have the same magnitude. But all the delta x, delta y, and delta z will be switched to the opposite sign. Okay, so that means that AB equals the negative of BA. Okay, the negative BA. This is weird. This is weird. So when we add the opposite, what we can do is rewrite that out as a difference. Okay, JC equals JE minus CE, okay, and that would be a subtraction statement, okay, to get from J to C. The subtractions are quite a bit tougher, folks. If you don't get the subtraction questions in the practice, that's okay. But now I do want you to get the addition ones for sure, but the subtraction ones are a little bit more challenging. Okay, one more. Let's look at a unit vector. So let's get a unit vector for W. So here's our formula for unit vectors. So we need to get the magnitude. How long is that vector? Well, we know the magnitude of vector W is going to be the square root of delta x squared plus delta y squared plus delta z squared. It's the three-dimensional Pythagorean theorem. So delta x is, so it's going to be 2 squared plus negative 1 squared plus 3 squared. Notice I don't even bother putting the brackets on if it's a positive value because I don't need to worry about that. But I always want to put brackets around the negatives because I want to make sure I don't accidentally subtract 1 squared. Okay, so by the way, that should have said that's negative 1 squared. Okay, so then finally we can say that W equals the square root of 2 squared is 4, 1 squared is 1, so that's 5. 3 squared is 9. 5 plus 9 is 14. So W equals root 14. I can get that in a decimal if I want, or I can represent this vector in absolute values. So W cap is the unit vector. It will have a length of 1. So since the length of vector w is root 14, if I want to make a unit vector, I just divide the original vector by root 14. So it's going to become this. So our unit vector is going to be 2 over root 14, negative 1 over root 14, 3 over root 14. Okay, and that is your unit vector. We can put that into a decimal. That's no problem. But if someone wanted to have it in an exact value, well, that's what they would do. Okay. All right, folks, so now we've gone through everything for 3D vectors, and you should be able to go through now and do the handout. It's only one page. It's a lot of questions. Well, not a lot, but there's quite a few questions. And you should be able to work through now and do some work with three-dimensional vectors. Good luck.